So in this video, I'm going to provide a recap of the theory required for system stability. So for a system to be stable, what we want is no poles appearing on the right-hand side of the imaginary axis. So if this is my imaginary axis, this is my real axis, we don't want any poles in this part. Okay. Another way of saying this is that we want no positive real components for our poles. Again, all that's telling us is that poles need to sit on this side of our imaginary axis, or even on the axis is okay. So I'm going to show you why this happens, and I'm going to do it with two examples, one where we have a stable system and one where we have an unstable system. So let's start with the stable one, and we're going to play with the transfer function x on f is equal to 1 on s squared plus 5s plus 4. So we should be able to go through quite easily and solve for the poles that we have down here. So you can do this with the quadratic equation, or Matlab or Wolfram Alpha, anything that you like. And if you go ahead and find what the poles are, remembering that that's just values of s where this bottom line goes to 0, we find out that it's going to be at -4 and -1. So that means that they're sitting out here on the real axis, like -4 maybe here, -1 here, which means that we have a stable system. But let me just show you what it's going to look like for the x as a function of time solution. So if I want to do that, let's pick an input. So let's say our input is going to be a unity step function, so 1 on s. That means that we can say that the output of our function x is equal to the transfer function multiplied by the input. So this moves up, which is 1 on s. And this is our x as a function of our Laplace variable. If we want to make it as a function of time, so this is with an s in here, all we need to do is perform the inverse Laplace transform, and I've taken this from Wolfram Alpha. Alright, so what we notice is that the poles that we worked out end up appearing in the exponentials. Okay, so -4 is -4 here. -1, this is like -1 here as well. Okay, so since we have negative poles, what we've ended up with here is negative exponentials. And this is important because if we want to plot our equation as a function of time, it's going to result in these exponential parts decaying away down to 0. So if we say we want to figure out the final value, so final value for our system, we know that in the time domain, we just need to apply the limit as time goes to infinity for our function, which is x as a function of time. And if we actually do that, so subbing in here, infinity is t, so e to the power of -infinity goes to 0. So that means that this term here is going to end up being 0. This term here as well, we've got e to the -infinity, it's going to work out to 0. And this doesn't have a t in it, so it's just going to remain as is. So that means that we end up with a final value of 1 on 4, or 0.25. And this is going to be a stable system because this is a finite value. And I'll show you in a moment what that looks like in Matlab, but you would expect that if you plot x as a function of time, it's just going to rise and then reach whatever point of 0.25. All right, it might have some overshoot or something like that in here, but the final value is going to be a very steady 0.25. So now let's look at the opposite kind of case, which is where we've got an unstable system. So it's going to follow the same kind of path, except that the transfer function that we're going to look at for x on f, I'm going to flip the sign so that this is a -5 instead of a +5. So if you go through and figure out your poles, again that's where the bottom line goes to 0, the values of s for that. This time what we work out is that we have poles at 4 and at 1, and they're both positive numbers. So if we go through this same process and give an example where we've got a unit input, and we go ahead and write out our equation for x as a function of s, all that's going to change is that we've got a negative in here for the transfer function. Alright, and then we want to go ahead and inverse Laplace transform it, so we get x as a function of time. Again, I've put this into Wolfram alpha. Okay, and this is what we end up with. And the same kind of pattern has occurred as what we saw before, where the poles end up appearing in the exponentials. We had a 4 here, we got a 4 here, we have a 1 here, we end up with a 1 in here. And this time what's happened is we've ended up with positives for the exponentials. Alright, so let's go ahead again and look at what happens when we do this final value theorem stuff. So again, we're looking at the limit as t goes to infinity of our x as a function of time. So if we substitute in infinity for t this time, we've got, it's negative sure at the front, but we've got e to the power of infinity. So e to the power of infinity, that is going to be a massive number. That's going to go to infinity. Okay? Same thing here, we've got e to the power of infinity again. Yep. Alright. And we've got 1 and 4. So, and these are slightly different as well. So basically what happens is the final value, it's just going to be an unstable system. Okay, because the final value is pretty much going to hit infinity. Okay, so let's have a look at what this actually is in Matlab. So if I jump over, I've written myself a little code. G1 is the first transfer function that we did, which should be stable. G2 is the second one we did, which should be unstable. So if we look at the stable one first of all, we can see that the final value approaches 0.25, which is what we were expecting. You can double check that if you right click and look at the characteristics and bring up the marker at the endpoint here. You can see it's 0.25, so we agree with that. If we now look at the one that's unstable, what we're going to see is that just as time keeps progressing and progressing and progressing, it goes higher and higher and higher in the value. And you can see that this is by 10 to the power of 24, so it's a massive number. It's shooting towards infinity. So this is definitely an unstable system because clearly it's never going to approach a final value as it should if it's a control system. So that's why if we jump back here, we always want to make sure that we have our poles on the negative side of our real stuff here, because that's going to ensure that we end up with negatives in the exponentials and that we again end up with systems which are stable. Okay. So the other part of this recap is looking at Ruth tables, which can be used to assess the stability of a system. So I'm going to do this with an example. I've set it out here. G is my transfer function. It doesn't matter what's on the top line, so I've just left it as a question mark. And the bottom line is what we're interested in because that's where the poles come from. So I've just set up a generic form here. And when we set out our table, what we're going to be interested in is the number of sign changes that we see in the first column of the Ruth table, because this corresponds to the number of poles on the right-hand side of the imaginary axis. And remember when we drew our diagram before, we said that even one pole on the right-hand side of our axis, so that's out here, is going to cause our system to be unstable. So essentially, if we have a stable system, we're going to have 0 sign changes in the first column of our Ruth table. Okay, so let's go through an example and fill out a Ruth table with this generic transfer function. So what we need to do first of all is assess the highest power of s that we have, and in our case it's s to the 4. And then we need to set up a row for every power beneath that, 2, until we get to 0. I'm going to set up some columns as well. Alright, so now we need to work on filling out the first 2 rows of this Ruth table, and those 2 rows relate to the coefficients in front of our different s powers in our transfer function. So we start with the highest one, which was our s to the power of 4, and the coefficient in front is a, so that goes in the first box. So an s to the power of 3 will be the next one, and that's going to be a coefficient of b, and it goes underneath. The next one we fill out, we need to jump up to the top row again, and we're going to have a c in front for that. We've then got d, which goes underneath, and e back up again. So you follow this kind of pattern as you move through each of your coefficients. Just watch out if you are missing a power of s term. So for example, if you pretend that this isn't here for a moment, when you go to fill out this box, instead of it being c, c would just be 0 for that case. So I guess that's a bit of a thing that can trip people up. Just be aware that even if an s power isn't stated in here, the coefficient is just going to be 0, so it needs to be entered into the table. So when you run out of coefficients, so e was our last one here, everything else can be a 0. So if it helps you fill out the table, everything else will be zeros along the end. So to fill this out, what we need to do is start taking some determinants. So we're only really interested in what's happening in the first column. So this is the only one that needs to be filled out completely. But some of these others are going to be necessary to be able to, again, fill out that first column. So let's say that we're interested in this box next. I'm going to give it a little 1 here and work it out at the side, what it actually is. Maybe I can use a different color. Alright, so what we need to do is we need to take a negative determinant. It's a bit bigger. So if we're interested in this cell, what we need to do is look in the first column for the 2 rows above. So that's going to be A and B, and they fill out the first column of our determinant. We then need to look again to the 2 rows above, but we want to look in the column to the right of this cell that we're interested in. So that's going to be C and D to fill out here. We then need to divide this determinant by the pivot element, and this is where you look at your cell of interest and you go to the row above and the first column of it. So that's going to be B. So that's our pivot element. So then usually these would be numbers, so it's just a case of evaluating what the new number would be. For a determinant, remember it's AD minus BC, so this would be that. And if you want to write it a little bit neater by putting in the negative, we get that. So this is what fills in this cell here. Alright, so next what we want to go for, to be able to do this one underneath, we need this one here. So I might try and pre-work this one, and we'll call it a 2. So, to work this one out, we need to go to the 2 rows above, and we need the first column. So again, it's going to be A and B. And this is our cell of interest. We now need to look for the 2 rows above, but we want the ones to the right. So it's going to be E and 0. This needs to be divided by the pivot element. So for this cell here, again, we need to go to the row above and the first column, which would be B. So we're going to get negative of A times 0 minus B times E divided by B. And this is going to all cancel down to just E on its own. So that's what goes in here. Alright, so let's come back down to this one here. We should be able to work it out now. I'll give it a 3. So we need the negative of the determinant. So that's going to be for this cell. We need the 2 above in the first column. So B and this thing that we already worked out. And then we need to the right, so D and E. And it gets divided by the pivot element, which is the row above, but the first column. So again, if you go ahead and simplify this, again, usually there'll be numbers, so it's not such messy algebra. You end up with that. So this goes in for here. Alright, So to be able to do this last one in the first column, we need this one here. This one, to get it, we need these and this. So if we come up here, this one's really easy. So if you do the negative of the determinant, you're going to have AB and 0, 0. So if you have 0, 0 in your determinant, let me quickly show you on paper. So it's going to be negative of AB 0, 0 on B. You're going to get A times 0 and B times 0, so that all goes to 0. 0 divided by B is still 0. So that one's easy. The same pattern kind of happens here because you end up with 2 zeros for your determinant. So this one we can now work out. I'll give it the 5. Go here. So for this one, it's going to be the negative of these two. And then to the right, we've got E and 0 divided by the pivot element. And this is pretty easy to work out because when you multiply these out, this times 0 goes away. You get this times this. This is the same as this. They end up cancelling. So you're just left with E in the end. So all that's left is to assess whether you have any sign changes. And for that, of course, you need some numbers to be able to assess whether they're positive or negative numbers. But all it is if, say, A and B are positive, this works out to be negative, then that's going to be one sign change from the positive to the negative. If all these are then negative, that's all you've got, because these just keep on staying the same. So there'll be a couple of examples where we'll do this with numbers, so you'll be able to see that in practice as well. So the last thing to mention is that there's a couple of special cases that we have for the Ruth tables. So one thing is that we can multiply any row by a constant number, and if you do that, it needs to be a positive, I should put in here. If you do that, it can make your life a little bit easier when you keep carrying down values through your Ruth table. So that's the only time I'd use it, is when you can make your life a bit easier. The next one is if a 0 is in the first column, replace it with a constant, which will have this little E thing, which is positive and very small. And that just helps you be able to carry down your sign change, because obviously if something is 0, then you're not going to be able to assess whether it was going to change from positive to negative. So that's all we need to do, just carry down this little E thing instead. And the last special case is if you get a row of zeros, you can replace the row with the derivative of the row above with respect to S. So again, there'll be an example of that in the other videos if you want to see that special case. Otherwise, that's all there is for the recap theory, and I hope to see you in the videos of the examples.